So let us continue with the intensity of the radiation under consideration. So in the previous lecture, we have seen that if the radiation is traveling along the third direction, then we have energy flux as follows. So it's a flux in the third direction, and it is 1/32 pi kappa times Hij dot times Hij dot. And Ij here run from 1 to 2. But in generic situation, if we have some region V where body is moving randomly, well, generically randomly, so they create radiation going in all directions, So hence our problem is to find Hij, which is traceless, and tangential to unit vector in the direction of radiation. So it should be, so we want to find such twiddle Hij. We have at our disposal Hij from the previous part of this lecture, which is approximately minus 2 kappa over 3 modulus of x Qij dot dot. So we want to construct from this vector something which is, well, it is traceless already because Qij is traceless, but we want to construct from it tangential to direction of radiation, arbitrary direction of radiation, to arbitrary unit vector Ni. It should be symmetric, of course, and traceless. So we want to construct such, from arbitrary Hij, we want to construct such a Hij twiddle obeying these conditions. So if we have at our disposal, Hij, the tensor that is tangential to n has the following form. It is Hij minus Ni Nk Hkj minus Nj Nk Hik plus Ni Nj Nk Nl HKL. So this one can easily check that this H perpendicular obeys, so H perpendicular Ij obeys the condition that it is perpendicular to n. Then transverse traceless part of it, H twiddle Ij, is the following. It is Hij orthogonal minus 1/2 delta Ij minus Ni and J times HLL orthogonal. So now having this, and using the fact that Ni squared is equal to 1, we have the following situation that Hij times Hij twiddle is equal to Hij minus 2 Ni and J Hki Hjk plus 1/2 Ni and J Hij squared. So this is what we obtain. Now we want to take the average. Well, if there is a random motion, the radiation more or less goes in all directions homogeneously, and we have to average all the possible directions of this unit vector Ni. So the averaging is done with the use of the following formulas. Well, the definition of the averaging is as follows. So if you have a bunch of vectors, Ni, Nil, Ni, N, well, and big N, this average is by definition is just integral over the solid angle over 4 pi of the product of ni 1 and in, where the components of n, vector n, I understand as follows. It's sine theta cosine phi, sine theta sine phi, and cosine theta. So you plug every component of this here and take this integral. This way you get this average. This is a definition. Well, the result of this calculation, say to take the average of this quantity, over all directions of n, we have to bear in mind that the result of the averaging for ni and j is just 1/3 of delta ij, and the average of ni and j and k and l is 1/15 times delta ij, delta kl plus delta ik, delta jl plus delta il, delta jk. Well, anyway, those who have been studying studying electromagnetic radiation and the motion of charges in inhomogeneous or homogeneous electromagnetic fields, in principle, should know this procedure and should understand the meaning of these answers. Well, anyway, as a result, this averaging, Hij twiddle, averaged is nothing but 2/5 Hij times Hij. So this is a result of the averaging. As a result, hence, the total intensity, which is the integral over d sigma I Ti0, is approximately, after and averaged, is approximately equal to 4 pi times x squared. So this is actually the area element at the distance x squared times 1/32 pi kappa times average of Hij twiddle dot, Hij twiddle dot. The fact that there are dots here doesn't change this fact. Well, it just leads to dotting here. And in all, we obtain the following expression, kappa over 45 times q ij triple dot times q ij triple dot. So this is a total intensity of the gravitational radiation in the non-relativistic quadrupole radiation. Well, let me, just to explain this formula, write what is d2 sigma I. It's just x squared times ni d omega. So to understand what's going on, we have a source of radiation here. We have a solid angle. We have this is d sigma, d2 sigma I. This is ni, unit vector in the direction of the radiation. And this is just modulus of x, this distance. So that's it. That's the formula we were going to obtain, and that's the formula we have obtained.